section 8.6, and our purpose statement, the student will be able to rewrite and simplify and evaluate radical expressions and rational exponents. Now, radical expressions, if you remember back from, we did these earlier in the year, radical expression is anything that has a, we call it, it's a radical sign, but we did mostly square root, but we can do cube roots or fourth roots or fifth roots and so on. And rational, remember rational exponents, rational is a fraction. So what we're going to do today is work with fractions in the exponent, which isn't hard to deal with, but it's new to you. So, first of all, when we take our radical sign, n is the index and a is the radicand. So the index, this would be read the nth root of a. So we could do the fifth root of 8. Okay, again, the index or root goes here, and then the radicand goes inside the radical sign. Now, we're going to look at different cases that we can work with radicals. The numbers and types of real roots. So we're going to have a case and then what the roots will be. So one case would be that we have an odd index, where the index in front is an odd number. And when we have that, we have one real root. If you remember back when we first did radicals, the square root of 25, remember, is plus or minus 5, because 5 squared is 25 and negative 5 squared is 25. But when you have an odd index, like here, the cube root of 8 is just 2. It's not positive 2 and negative 2, because 2 cubed is 8, but negative 2 cubed would be negative 8. So we can do negative numbers. It doesn't make any difference if the radicand is positive or negative. It just would be the cube root of negative 8 would be negative 2, because negative 2 times negative 2 times negative 2 would give you a negative 8. So that would be when you have an odd index, you have one real root. An even index and a positive radicand. So where we have an even index, in this case 4, and the number inside is positive, the radicand 16, now we go back to where we have two real roots, because 2 to the 4th power is 16 and negative 2 to the 4th power is 16. So both cases work. We could have an even index and a negative radicand. In that case, you have 0 real roots, and the reason for that is, remember when we did square roots, they weren't real answers of negative numbers. Took square roots of like negative 25, it was plus or minus 5i, where you put in the imaginary unit. So we can't do fourth roots of negative 16. We have no real roots, because there's nothing that times itself 4 times that will give you a negative 16. You can go 2 to the 4th power is 16, and negative 2 to the 4th power would be a positive 16 also. So you can't get a negative number in there. And then the last case would be, what if the radicand of 0? So it wouldn't make any difference what this index was. If it's 0 inside, the only possibility would be that we would get 0 out, and so you would have one real root. So this gives you all your possibilities for cases that occur with radicals. So properties of nth roots for a greater than 0 and b greater than 0. Now, again, we've done this before this year. We did it with square roots, but now it works the same with all of them. The nth root of a product is equal to the product of the nth roots. All this tells you is if you have something inside here, you can break it into parts. And they can be multiplied together, or you could break it up. And I'll show you an example of that in just a second. So the nth root of a times b could be broken into the nth root of a times the nth root of b. So an example would be, let's take the third root of 250, x to the 12th, y to the 14th. All right? So what we have to do is break this up into cube roots. And for some of you, it might be helpful to make a chart. So if I was to make a chart, what I'd want to do is, like, say, n is 1, 2, 3, 4, 5, 6, 8, 9, 10, and so on. And so the n squared then would be 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. And then I could do the cube root, or n to the third power. So that would be 1, and just multiply these together. So 8, 27, 64, 125, 216, and so on. You're probably not going to have anything that gets much bigger than this. We could go 63, 28, 343, 512, 729, 1,000. But you're probably not going to get that big, but it's easy to make the chart out as far as I need to. So 1, so now you would take n to the third times n, so that would be 16, 81, 256, 625. Again, you're probably not going to get bigger numbers than that. And if we go to n to the fifth, again, we're just going to take n to the fourth, so that'd be 1, 32, 243, 1,024, and so on. So you can make that chart out to use. Again, if you need this, you can pause it if you want to write it down, or you can make it out yourself. But I'm going to erase this so we can get back to this problem. So there's lots of ways you can do this. I'll show you basically 3 ways that the book would have you do it, or that I do it. The book would have you break it up into parts. And so we take the cube root, and then what you want to do is break this number up into things you can take the cube root of. So if you look back at that chart, we can take the cube root of 125. So I could break that into 125 times the cube root of 2, because 125 times 2 is 250. With variables, it's really easy. The power has to be divisible by the index. So 12 is divisible by 3, so I can break that into 3 times x to the 12th. And then y to the 14th is not divisible, but I can break the y to the 14th up into y to the 12th times y squared. Because remember, when you multiply, you add exponents. So that would be the same as y to the 14th. Then you just simply break down the parts. Since I can take the cube root of this, 5 comes out front. I can't take the cube root of 2. Again, with variables, you just divide the powers. 12 divided by 3 would be x to the 4th. So that's gone. 12 divided by 3, that would be y to the 4th. And that's gone. And then anything that's left that I can't take the square root of stays inside. So the cube root of 2y squared. And that would be the simplified form. So this is the way the book shows it on most of the problems, is to break it up this way. And that's fine. What I do, when I do it myself, would be I just break it down up above. So I would go 125 times 2. I can do x to the 12th, and then I would break this down into... And then I do the same thing that I just did. I said, oh, I can take the cube root of 125. That's 5. I can take the cube root of x to the 12th. That's x to the 4th. I can take the cube root of y to the 12th. That's y to the 4th. And then whatever I haven't crossed out goes inside. So it doesn't make any difference which way you do this. It's fine. Another thing you could do is you could go back to your factor tree and break 250 up into 25 times 10, and that into 5 times 5 and 5 times 2. And to take the cube root of it, you need 3 of them. So I've got 3 5s, so that means I can pull a 5 out front, and then whatever I have left would stay inside, and then you'd work with the variables just like we did before. So that would be another way to do it. Whichever works best for you. So that was if we have something multiplied. The quotient property of roots, the nth root of a quotient is equal to the quotient of the nth roots. Simplified, it's pretty easy when you look at an example. the nth root of a over b, so when you have a fraction inside the radical, you just break it up into its parts. So the nth root of a over the nth root of b. So again, if we look at an example, let's take the cube root of 27x to the 5th over 4. Okay? So the first thing we're going to do is split this into two parts. So it's the cube root of 27x to the 5th over the cube root of 4. So we're going to simplify the numerator first. I can take the cube root of 27. So I'm just going to put 27 up here. I can't do 5 is not divisible by 3, but I can break it up into x to the 3rd times x squared. So the cube root of 27 is 3, so that's gone. The cube root of x to the 3rd would be x. And then I can't take the cube root of x squared, so I'm just going to put the cube root of x squared there. Now, on the bottom I have the cube root of 4, and I can't take the cube root of 4. But if you remember back when we first did these with fractions, if you remember back, like if I had 3 square root of 2, you can't leave a radical in the denominator and have it simplified. So to get rid of this, we would multiply by the square root of 2 over the square root of 2, and get 3 square root of 2. And then square root of 2 times square root of 2 is the square root of 4, and the square root of 4 is 2. And so we get that. So what I get from people when they first start doing this, they want to multiply by the cube root of 4 over the cube root of 4. But if I do that, look what happens. If I did the cube root of 4 over the cube root of 4, on the bottom I get the cube root of 16, and we can't take the cube root of 16. So we have to multiply this by something that I can take the cube root of. And so if you look back at your list, what you want to look for is the first thing that 4 goes into that I can take the cube root of, which would be 8. So what do I have to multiply 4 by to get to 8? That would be the cube root of 2. So on top, I get 3x, and then I get the cube root. Remember when you multiply radicals together, as long as the index is the same, you just multiply what's inside. So 2x squared. And then the cube root of 4 times the cube root of 2 would be the cube root of 8, but the cube root of 8 is 2. And that gets rid of that radical in the denominator, which you have to do. So they get a little complicated, but if you take it one part at a time, hopefully you shouldn't have trouble doing that. The next part is on rational exponents. Now, when you're working with rational exponents, this is what the book has on there, is the exponent 1 over n indicates the nth root. And the exponent m divided by n indicates the nth root raised to the nth power. So what we're doing on this, it's really pretty simple, is that if we have 5 to the 2/3 power, and I want to switch that to radical form, okay? So I'm going to write this as a radical. The denominator is your index. The base, 5, is your radicand. And your numerator is your exponent. Now, you can see that I have this written two different ways here. The nth root of a to the m, which is the way I wrote it here, or I could write it this way and put the squared outside. Both of them give you the same answer. It's just on some problems it's easier to do this way than to do this way. So let me show you an example. If I took 8 to the 3/5 power, and I was to write this now in radical form, That would be, actually let's do 5/3, 8 to the 5/3. That would be the third root, okay? Denominator is our index, the base is our radicand, 5 is the exponent. So if I was to do this the way it's written, I would have to take 8 to the 5th power, which you can do on the calculator, and then take the cube root of that. But if I did it this way, most of us can probably do this in our head. The cube root of 8 is 2, and so 2 to the 5th power, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And so this equals 32. So you can do it either way. You can do 8 to the 5th power and then take the cube root of it. But if you can take the root of it, the radicand first, it just makes it easier. The other thing you can do is you can put this into the calculator. And when you do it in the calculator, you just do your exponent symbol, and now you have to do the fraction. The thing you have to be careful of is that if you must, at least on most calculators, put that in parentheses. Because if you write it this way, without the parentheses, it will take 8 to the 5th power and then divide it by 3. So you want to make sure you include the parentheses on that. So properties of exponents. Now, these are all the same as everything we've done before. We just haven't done it with fractions before. As an example, x to the 2nd times x to the 3rd. Remember, when you multiply and the bases are the same, you add exponents. So x to the 5th. Well, it's the same thing here. Product of powers, same base, add exponents. The only difference now is that they're fractions. 2 to the 3/5 times 2 to the 2/5 is 2 to the 5/5, or 1. 2 to the 1st, which would be 2. Quotient of powers, same thing. Remember, if we had x to the 5th over x to the 2nd, when you divide, you subtract powers, so that would be x to the 3rd. So the same thing happens here. We subtract exponents. So this is 5 to the 2/3 over 5 to the 1/3. 2/3 minus 1/3 would be 1/3, so it would be 5 to the 1/3. Power of a power. So this would be if I have x to the 5th cubed. Remember, a power to a power, we multiply powers. So it would be x to the 15th. So here is an example with fractions. 2 to the 2/3 to the 1/3. So we multiply. Remember, when you multiply fractions, you multiply straight across top and straight across the bottom. So 2 times 1 is 2. 3 times 3 is 9. So 2 to the 2/9. Power of a product. If we have a power outside, remember, that distributes to both of those. So instead, you could go 8 times 27 on your calculator and then take the 3rd root of that. But you can distribute that and go 8 to the 1/3 times 27 to the 1/3. So the cube root of 8 is 2. The cube root of 27 is 3. So 2 times 3 is 6. And the same thing if it's a quotient, a fraction. 16 over 81 to the 1/4. The 1/4 power affects both the numerator and the denominator. So the 4th root of 16 is 2, and the 4th root of 81 is 3. You could type this into your calculator. You'd get a decimal, but it would be 0.666666. So all the rules are the same as what we've used before. The only difference is now we're going to have fractions up there instead of whole numbers. Your assignment for today, page 615, numbers 31 to 57, the odds. Hopefully this helps you. Again, I would make that chart out or copy it down from before and use that because it makes it a little faster than having to do it on your calculator or to make a factor tree. So, good luck.